everyone. In this video, we're going to look at the derivatives of some exponential and logarithmic functions, which is going to involve looking at some limits as well. So let's consider an exponential function, y equals some base b to the power of x, and we're going to assume that b is a positive number and that it's not equal to 1. Because if it's equal to 1, then we just have the constant function y equals 1, which isn't very interesting. So going back to first principles, the derivative of this function is going to be the limit as h approaches 0 of b to the power of x plus h minus b to the x over h. I'm going to factor out b to the x. It doesn't involve h, so it's not impacting the limit in any way. So this is b to the power of x times the limit as h approaches 0 of b to the power of h minus 1 over h. So this limit, if it is a constant, will be the coefficient. So the derivative of b to the power of x will be b to the power of x times some coefficient, depending on what this limit is. So let's actually go explore some values of b and see what this limit could be. We're not going to algebraically figure it out. It's a little bit tricky, but we're going to sort of play around with. So let's look at what is happening as h approaches 0 for some values of b. So specifically, let's start with b equals 0.5. Now, this graph kind of looks like there is actually a point there. Desmos doesn't do this super well, but actually if I hover over it, I can see that, oops, when x equals 0, y is undefined. But I can nevertheless sort of see where it's close to. So if I see that I have values that are close to 0, that I have values of y that are kind of close to negative 6.9-ish. So let's say that our limit is about 0.69, negative. Now let's look, if b equals 1, I just mentioned that's not very interesting. So if I put b equals 1, that's why it's not in our table. B equals 1 is just a constant function here. The limit is just going to be 0. And so the derivative would just be 0. That's not very interesting. But let's look at 1.5. So if b is 1.5, again, if I hover over here, I can see when x equals 0, the y value is undefined. So the limit doesn't really, so the value doesn't exist. But I can see that for x values that are close to 0, I have a y value that's close to 0.4. So this limit is about 0.4-ish. All right, so moving on, when b equals 2, when b equals 2, again, it's going to be undefined at that value, but so when x equals 0, it's undefined, but when x is close, we're at about 0.69-ish again, so positive 0.69. And let's look at 2.5. So we'll kind of rush through these ones a little bit. 2.5, our limit is going to be about 0.9, let's say about 0.9. We don't need to get too precise. We're just looking for a pattern here. When it is equal to 3, we've got about 1.1-ish, let's say. And when b, so remember this is the base of the exponent, is equal to 3.5, then we've got about 1.2 somewhere in there. So 1.2. So what this means is that, that coefficient here, so if I'm deriving the function y equals 3 to the power of x, for example, the derivative is going to be about 1.1 times 3 to the power of x. If I'm deriving y equals 1.5 to the power of x, then the derivative is going to be about 0.4 times 1.5 to the power of x. So some coefficient on the function itself. But what I can see sort of more importantly here is that somewhere in this region, the limit would be 0. Or sorry, limit would be 1. For some value between 2.7 and 3. And this is where e comes from. E is the base that is chosen such that this limit equals 1, such that the limit as h approaches 0 of e to the power of h minus 1 over h equals 1. That's why we refer to e as the base of the natural logarithm. It's why we call it natural. It's because it's what happens when that limit is 1. So in other words, the derivative of e to the power of x would be e to the power of x. So if y equals e to the power of x, dy dx is therefore going to equal e to the power of x times this limit, which we have specifically chosen this base to be 1. We've specifically chosen this base so that this limit is 1, which means that this is just e to the power of x. So we explicitly choose the value e, which is about 2.718 or so. So that's why we choose that. So the exponential function with a base of e is its own derivative. Every other exponential function has to have some multiplier, some coefficient, but e is its own derivative. Now, if the base isn't e, so let's say if b does not equal e, well, then we can still use this fact to figure out what that would have to be. So let's say, for example, y equals 2 to the power of x. But I can express this with any base I want. I can change my base. So if y equals 2 to the power of x, this is the same thing as y equals e to the power of ln 2 of x. Because e to the power of the natural log of 2, because e and the natural log are inverse functions of each other, is just 2. So now this is the same thing as e to the power of x times ln 2. I can derive this using the chain rule. So the derivative of 2 to the power of x with respect to x is going to be e to the power of x ln 2 times ln 2, or in other words, 2 to the power of x times ln 2. But this basically gives us the secret. So if I go back to this table, and you certainly can verify this, I'm not going to bother going through it, but it was that change of base we just did. This value is the natural log of 0.5, the natural log of 1.5, the natural log of 2, the natural log of 3.5. That coefficient is the natural log of the base. So very, very generally here, the derivative of b to the power of x with respect to x is b to the power of x times the natural log of b. And that's why e is our preferred base, because the natural log of e is just 1. All right, now knowing that information, we can figure out what the derivative of ln x is without having to go to first principles, because we can rewrite this function as e to the power of y equals x. Just rearranging this logarithmic equation into exponential form, which I can now derive implicitly. So e to the power of y times dy dx equals 1, which means that dy dx equals 1 over e to the power of y. But e to the power of y is equal to x, so 1 over x, which means that the derivative of the natural log of x with respect to x is 1 over x. Again, because we can change bases, I can now derive any logarithmic function with any base. So if y equals log base b of x, this is equal to the natural log of x over the natural log of b, where the natural log of b is just going to be a constant. So dy dx is simply going to be 1 over ln of b times the derivative of natural log of x, which is 1 over x. Or in other words, to state this more generally, the derivative of log base b of x with respect to x is equal to 1 over x times the natural log of the base. So again, this is why we prefer a base of e, because then we don't have to worry about that coefficient.